Today we will talk about the dosimetry, how to calculate the equivalent dose, the absorbed dose from different sources. We already started this topic during the last seminar, and today we will continue because it is important topic in any areas when we are working with sources of ionizing radiation in nuclear facilities or in nuclear medical centers. In any case. So last time we already solved this task when we have a source of ionizing radiation like cesium-137. We know the activity of this source, we know all the characteristics that is expressed as a gamma constant for this radionuclide. We know the distance to work with this ionizing radiation source and the time during the day that we are spending working with this source. But it was only one example when we have the ionizing radiation source with only one gamma line. That means that the gamma quanta that are emitted, they have only one energy, and for cesium it is 662 kiloelectron volts. With the calculation of the equivalent dose, and we know the limits for work during the day, the maximum dose that is allowed. And with this we calculate the attenuation factor, and if we know this attenuation factor that we have to reach and the energy of gamma radiation of gamma quantum, then we can calculate not calculate, but just take the number, and this number, it is the thickness of a lead shield. And again, it was quite simple in the case of cesium-137, because it is only one energy of gamma quanta, and we know this attenuation coefficient, and thus we know the thickness. But let's try to solve another task when we have also a source of ionizing radiation with one radionuclide. In this case, it is cesium-134, and this radionuclide has three different gamma lines that are emitted with different intensity, but we have to calculate this lead shield to ensure the safe operation with such source of ionizing radiation. In this case, we have to calculate the density, the thickness of such a shielding for each of these gamma quanta, and then compare them between each other and choose what are the main lines, the main concurrent lines, and or competitive lines, and then there are some other steps for calculation of this thickness, the optimal thickness. So, okay. Let's start to solve this task. We know the energy of gamma quantum, for example, 567 kilo electron volts, and we have in reference books or in databases such data about the gamma constant for gamma quantum with different energy. These energies are in mega electron volts, so it is 500 kilo electron volts, 600 kilo electron volts, etc. And knowing these values for gamma quantum with certain energy, we can recalculate these values for other energies specified for our radionuclide. For example, let's calculate or assume these values for something like here, gamma for our energies. First of all, it is for 567 kilo electron volts. So we have these two numbers for 500 kilo electron volts and for 600 kilo electron volts. And thus we have to calculate somehow these values for 567. In this case, we can easily take the difference between 22.6 and 18.9. So let's take this difference, 22.6, just a moment, minus 18, oops, I will take that one. 18.9, and it will gives us 2.7. We can divide this 2.7 by 100 and then multiply it by 67. It will be the difference between the 500 kilo electron volts and 567, and it will be equal to, oh sorry, it's not 2.7, it's 3.7, yeah. So it will give us 2.48, and thus our gamma constant for this energy will be 2.48 plus 18.9. So it will be 21.38. So the same for 604 kilo electron volts. So we can take, we can also calculate it. Let's calculate to be sure that we didn't miss any significant numbers. So it will be also 26.2 minus 22.6 divided by 100 multiplied by 4. So it will be a very small addition, but still. So it will be 22.74. And for our last value of gamma, energy of gamma quanta, let's take, it will be 29.3 something. Okay. Now we know the gamma constant for the entire radionuclide, and from this we have to calculate the partial values of this gamma constant. Let's mark it with asterisks. And in principle, it's just the product of our gamma constant for our energy of gamma quantum and the intensity of this gamma quantum. So let's just multiply these two numbers, and what we will give. So in this case, it will be 4.9. I will write the round numbers, so it will be easier for us. 22.1 27.2. Okay. So let's keep it like this. Now let's calculate the attenuation factor. In how many times we have to reduce the dose that is created by our source of ionizing radiation at distance of 50 centimeters. I hope that you remember that this equation. So it is equivalent dose. We multiply this. So this is coefficient to go from the air to the biological tissue. Then there is a gamma constant for our radionuclide multiplied by the activity divided by the distance. Yeah, and we will calculate not the dose, but the dose rate. So let's write it as a dose rate or intensity of our equivalent dose. And we simply put all these numbers. Gamma in this case it is 57. Remember that atto means 10 to minus 18 gray per square meter per second per becquerel. So we convert 4 gigabecquerels in becquerels, so it is 4 to 10 to 9. And we divide it by distance, square distance, in meters. Because here we have this unit in minutes, in meters, sorry, and thus we have to recalculate it. And let's calculate this intensity or dose rate not in second but in 1 hour, and it will be, so it is number of seconds in 1 hour. So, and we will obtain, so it will be 3.6 10 to minus, so on, minus 3 zievert per hour. The limit for our dose rate at the working place, so H limit is equal to 6 micro zievert per hour. Thus, it is 6 to 10 to minus 6 zievert per hour. That means that we have to recalculate it so that our coefficient will be 3.6 10 to minus 3 divided by 6 to minus 6. So it will give us simply 600. Okay, now let's calculate the attenuation coefficient for each gamma line. How to calculate it? This we can calculate quite easy. It will be the overall attenuation coefficient multiplied by the relationship between the, let's put it here, between the partial gamma constant for each line divided by the overall gamma constant. So in this case it will be 600 multiplied by our partial gamma constant divided by the overall gamma constant. So let's calculate it for each line. And now for each line we have to find the thickness of lead shield in centimeters for each of these attenuation coefficient. We have to remember that when we find the thickness of the shielding, we use the doubled K value to ensure the safe operation of with our ionizing radiation source. So, and now we will go to this table. Yeah, unfortunately it overlaid, but we will find it. So for each energy we have to find the thickness in centimeter for the doubled K value. So it will be in the first case the energy is 567 kilo electron volts, so it will be in between of these two numbers, and we have to find this number for the K value of not 51, but let's take 100. So, and just a moment. And it is the value of let's say around 3.8 centimeters, or approximately 4 centimeters. Let's take this number. Then the next energy, it was, let's go back, was 600, more or less a round number. So we are finding this 600 kilo electron volts, and we are looking not for 232, but for not for 232, but for 465. So 465 will be very close to 500, and so we can calculate it more precisely. But in this case, it will be 5.2. Yeah, 5.2 centimeters. Yeah, something like this. We can easily recalculate it as again we can take the difference between 500 and 200. It will be 300 K values. We can divide this difference between 5.2 and 4.5 by 300, and then multiplied it by 265, and then it will be approximately 4.4 centimeters. Yeah, it's better. And now the same is for 286. We multiplied it by 2, so it will be 570, and we can find it as so for energy of, one moment, it was the energy, oops, the energy was 800, 800 kilo electron volts, yeah. Okay, and we can find it somewhere here, yeah, between 7.4 and 8.2. So it will be very close to 7.5, let's say, centimeters. Okay. So now we have these thicknesses, the thickness values for all of our gamma lines, and now we can see that there is one main line with the required thickness of 7.5 centimeters. The main competitive line with the thickness of 4.4 centimeters, and the weakest line with the required thickness of around 4 centimeters. So now we have to compare these values. How to calculate now what the thickness is will be efficient? Should we summarize all these thicknesses, and then we will obtain quite a thick lead shielding that will be definitely enough. But when we calculate the thickness of lead shielding, it is not only the question of safety operations, but also some economical aspects of our working conditions. Thus, we have to find the optimum between the very thick lead shielding and economically reliable thickness, and to ensure the safe operation. In this case, the next step, we double our K values. So we will neglect this line. We double our K values for each line. Let's take these numbers. And now we are finding this D values for these values. So we double them again and find the D values for such values. So it will be around 900. So again, we are looking for the energy of 600 kilo electron volts, and it will be around 5.7 and 5.2, so it will be 5.6 centimeters. In this case, and in the case of 800 kilo electron volts, it will be around so a bit more than 1,000. So it will be not here between 8.2 and 9. So it will be, let's say, 8.3 centimeters. Okay, now let's go back. Oops. So what next? Now we will find these delta values. So that is called the thickness of a lead shielding that will lead to reducing of our equivalent dose in 2 times. Because we doubled our K value and we calculated with this D thickness. Now we will take the difference between this and this. It will be 1.2 here centimeters, and here it will be 0.8 centimeters. And for further analysis, we will take the maximum value around these 2 values. So what next? Now we compare this value with other D values. So first of all, we can take the difference in D value between the main line and the competitive line. So this delta D will be 7.5 minus 4.4, that will give us 2.9 centimeter. So we have two values for further analysis, this 2.9 centimeters and this 1.2 centimeters. And we should take these conditions. So if the differences in D values for main line and competitive line is equal to 0, so they are the same, then the overall, the total thickness of our lead shielding will be calculated as the D value for our main line plus delta of the half-life of attenuation. This is not the case for our task. So the next condition, if the difference in D values for main line and the competitive line is less than this half-life delta, not half-life, half attenuation delta. Again, our difference in D values is 2.9 and our half attenuation delta is 1.2, so it is not our case again. And our case is that the difference in the D values between the main line and the competitive line is more than delta for half attenuation. And in this case, the total density, not density, the thickness, total thickness of the lead shielding simply equal to the D values for the main line. So in this case, if we will take the thickness of the lead shielding that is equal to 7.5 centimeters, it will be enough to ensure the safe operation and to reduce all the doses, all the energies that are coming from other lines as well. It is not always the case. Then we have the thickness of the lead shielding that is simply equal to the minimization of the most energetic line. For example, if the intensity of this line would be, let's say, 10%, then the K value would be 10 times lower, and the K values also, and thus this thickness would be much smaller. And we, in this case, we should take all these considerations and recalculate not recalculate, but take these numbers for our thickness of the lead shielding. So I hope that it is a first step in understanding how all this shielding equipment are calculated. Again, it is in this case quite simple calculations, and if there is a very complex source when we have different radionuclides with different gamma lines, we have to take into account all their properties, their activities, to calculate the dose that they produce at certain distances, calculate all these attenuation factors, and to assume the D values in this complex system. But at least the first steps should be clear in this case. The next task. Estimate the equivalent dose during the working operations with the ionizing radiation source of sodium-24 with the known activity at certain distance and time. What is the problem with this source? The sodium-24, it's not only a gamma emitter, but also it has quite so the beta particles with high energy. So we have to calculate the dose rate, so the dose rate from both beta particles and gamma quanta. And from this, we will calculate the total dose rate. Why we calculate the dose rate but not the dose at this point? Because the half-life of sodium-24 is small, so it is 15 hours, and it is comparable with the time of working. So if we will estimate this dose rate only with the activity at the initial time, so 1 megabecquerel, and we will take only this activity. That means that we didn't assume the decay of the sodium-24, and we will overestimate the equivalent dose from this source. Sodium-24 is decaying, and thus the activity is decreasing, and also the dose rate is decreasing with time. To take into account all of these processes, we have to calculate the dose. Sorry, dose. It's a D. Dose as a function of dose rate with time. So in this case, dose will be calculated as integral from our initial point in time, it is time equal to 0, to our 6 hours, and it will be our dose rate calculated at initial moment, and dose rate will also decrease with time as the activity. That means that it will be exponent. So fortunately for us, it's quite easy to calculate because integral of the exponent it's simply the same exponent with the corresponding coefficient, and thus it will be with the limits of integration from 0 to 6. Okay. So, but now we have to calculate, the dose rates from beta particles and gamma quanta. And last time, during the last seminar, we already used this equation. It is a reminder for this specific equation. So in the case of our beta particles, it will be 1.6 to 10 to minus 10, because we will use the energy of beta particles in mega electron volts. So activity, we know the activity, so it is 1 megabecquerel, so it is 1 10 to 6 megabecquerel. Time, we will not use time because dose rate, it is dose divided by time, but we will take 4p and distance squared, and the distance we will take in centimeters, so it is 30 squared. And then there is only one beta decay, so it is only beta minus decay, and thus intensity is equal to 1. We will not take it. We will take the average energy of the beta particles, and it is 1 39 mega electron volts. I will just remind you here, it is mega electron volts, divided by the maximum range of our particles, and the maximum range is 0.613 gram per squared centimeter. So it is also squared centimeter. It is becquerel. And then the exponent we multiply it by the exponent with minus 0.1. Distance is 30 centimeters, and the density of air is equal to 0.01012 gram per cubic centimeter. So we have everything from our equation. I didn't forget anything. So let's calculate it. The same for, more or less the same for gamma quantum, but in this case we have to recalculate it with this coefficient. Don't forget about this coefficient. It is very important to recalculate the absorbed dose to the equivalent dose. Activity is the same, 10 to 6 becquerel, divided by the, in this case, we have to convert it to meters, squared meters, because our gamma constant is equal to Atto Gray, so 10 to minus 18 per squared meter divided by second and becquerel. So 0.36 10 to minus 9 zeros per second. So you can see that in this case, at short distances of 30 centimeters, we will get the highest dose rate from the beta particles and not from the gamma quanta. So now we should calculate the total dose rate at the initial moment when the activity of our ionizing source is equal to 1 becquerel. So it is simply the sum of these two dose rates. So it will be equal to 1096 10 to minus 9 zeros per second. So now we have everything to calculate the dose rate that we will get during the 6 hours of working operation. So if we will write this equation further, it will be this multiplied by 1 minus exponent minus lambda multiplied by 6 hours. And further, so I write it here. So it will be P0 divided by logarithm 2. The half-life will go here. And here it will be 1 minus log 2, natural logarithm 2 multiplied by 6 divided by 15. So where 15 is the half-life of our radionuclide. In this case, there is no need to convert hours to seconds because the time is also in hours. But here we should convert our 15 hours, the half-life of our radionuclide, to seconds because we calculate the dose rate in zeros per second. And thus, the D, I will rewrite it, D will be equal to 10 to minus 9 zeros per second multiplied by 15 and seconds in hours, so second will be divided by logarithm 2, and then 1 minus exponent minus log 2, 6, 15. So the received equivalent dose will be, so it will be equal to 2 10 to minus 4 sievert. Or if we express it in microsievert, it will be 200 microsievert. And we remember that the equivalent dose that are allowed during the working day is equal to 72 microsievert. That means that it will be not a safe operation during the working day. Interesting moment again that we can see that the main dose rate at this distance will come from the beta particles. Let's now assume what is the thickness of, for example, aluminum shield we should use for beta particles. We know that the maximum range for these beta particles is equal to 0.613 grams per square centimeters. Thus, if we recalculate it to the linear thickness, we have to take simply this equation. I will write it here. So L, the linear range, L maximum, if we will take aluminum, it will be simply maximum range divided by the density of our material. So in this case it is 0.613 divided by 2.7. So it will be equal to 0.23, 0.23, and it is centimeters. Thus, the maximum range is equal to, let's say, 2.3 millimeters. That means if I will take the aluminum shield with the thickness of, let's say, 3 millimeters, it will be enough to stop completely all the beta particles that are emitted from this source. And thus we will reduce, let's say, 90% of all the dose rate. If we do it, that means that our equivalent dose will be equal not to 200 microsievert, but to only around 20 microsievert or something like that. In any way, it will be lower than the maximum allowed equivalent dose. And with using of such a thin shield, we can ensure the safe operation with such radionuclide. Or if we will use just a reservoir with water, the density of water is only 1. That means that the maximum range in water will be 6.1 millimeters. So that means that even the commonly used cuvette for spectrophotometry, if it will be very long cuvette, will be efficient for stopping all the beta particles from our radionuclide. Okay, let's go further. Now let's imagine that the alpha particle, alpha emitting radionuclide, somehow introduced inside the body by inhalation or ingestion, And let's calculate what is the dose that is released or absorbed in the tissues due to the alpha decay of our radionuclide. So there is some radionuclide with known activity and energy of emitted alpha particles with the intensity of 100%. That means that all decays undergo with the emitting of alpha particles. We know the density of the biological tissue that is close to the density of water, and we know the maximum range of these alpha particles. So in this case it will be quite easy calculations because by definition the absorbed dose, it is the energy that is absorbed in the matter with mass m, and it is the ratio of energy by the mass. Energy, how we calculate the energy? It's simply the number of alpha particles multiplied by the energy of alpha particles. Mass is simply the product of density and the volume of our object. In the case of alpha particle and our source, again, we assume that all the radiation goes isotropically to the sphere, and thus all the energy will be absorbed in the sphere with the volume that is equal to 4 divided by 3 p cubic radius. And in this case, this radius is equal to the range of alpha particles. We can express this range knowing maximum range of alpha particles and dividing by the density of our material, and it is 1 gram per cubic centimeter, and thus the radius will be equal to the 0.0056 centimeters. So now let's put all this, and what is the number of alpha particles? It is simply the activity of our radionuclide multiplied by the time of the observation, and that's it. So divided by 4.3 per cubic and the density. So, and let's, as far as we need to calculate the dose rate, it is simply dose divided by time. So we will use this equation simply without the time. So let's calculate it. So it will be activity 10 kilobecquerels, kilo means 10 to 3. Energy of alpha particles 6 to 6 electron volts, but we have to convert it to standard units in C, so it is 1.6 10 to minus 19, because 1 electron volt is equal to 1.6 to 10 to minus 19 joule, so it is joule, and so it is becquerel, sorry, and divided by 4.4 0.0056 centimeters, we should convert to meters, again to the standard units, so it will be 10 to minus 2 squared, and also it is product of the density. And density is equal to 1000 kilogram per cubic meter. So here it's meter. Oh, sorry, it's not squared, it's cubic. Finally, we will have only joule per kilo, that is equal to gray. And thus, so we have all the numbers. Let's calculate. 13 gray per second. So it is extremely high dose rate. If we try to recalculate it to equivalent dose, we have to, or let's say the rate of equivalent dose. It will be the Wien factor for our radiation type multiplied by the dose rate for the absorbed dose. So for alpha radiation, the Wien factor is equal to 20. So finally, we will have something like 260 sievert per second. That means that even 1 second will be enough to kill all the cells that are located in the sphere of around this source of ionization. So from these calculations, you can see that how it is dangerous and hazardous to have alpha emitters inside the human body, because locally it creates a very high dose rate. Of course, if we recalculate it not by the mass of this very small sphere, but by the total mass of the human body, by, for example, 80 or 90 kilos, the dose rate will be very small and even negligible. But locally, the dose rate will be very high. That's why alpha emitters can be used for treatment of cancer diseases to kill the cancer cells, because again, locally the dose rate will be very high, enough to kill all the cells around this source of radiation. So let's go further. Okay, the next task is also related to the internal radiation dose that is created inside the human body, but in this case we put the radiation source for treatment, for diagnosis of cancer disease. For this, we use quite important molecule, fluorodeoxyglucose, FDG, that is labeled with the fluorine 18. It is this molecule even called the molecule of millennia, because it is the most used molecule in positron emission tomography, and also it helped to save I don't know, millions of lives due to the very precise diagnostics of cancer diseases. So for this medical procedure, we introduce the radiopharmaceutical that contains fluorine 18, and of course it is a very convenient method for diagnostics, but we also have to ensure the safe operation for the patient and also for medical personnel. In this case, we will calculate the dose, the equivalent dose for our patient with the body mass of 95 kilos. We know the activity of the introduced radiopharmaceutical. The half-life of fluorine 18 is quite short, is 110 minutes, sorry. And also there is a biological half-life, so that means that half of the component of the compound will be released from the human body due to the natural processes in 90 minutes. And there is some characteristics of the decay of fluorine 18. And we have to assume what is the dose, equivalent dose that is created in the human body if all the beta plus particles they are absorbed in the body, and as far as it is beta plus particles, it is they are positrons. That means that they annihilate and they produce 2 gamma quantas with the energy of 511 kilo electron volts. And we assume that 50% of the generated photons of generated gamma quanta will leave the body. And the energy released due to the electron capture, we can neglect it. So again, we have two components that creates our dose rate. It is beta particles, in this case beta plus particles, and gamma quanta. We also assume that the whole activity is distributed evenly, and all the energy released by the beta particles, for example, is absorbed by the human body evenly. And in this case, we can calculate the dose as the whole energy released by beta particles and divided by the whole mass of the human body. Let's write it here. So again, let's calculate the dose rate first. A dose rate in initial moment as a sum of dose rate from beta particles and gamma quantum. The dose rate from beta particles. Again, it is the number or activity of our radionuclide that emits beta particles with a certain intensity. It is 97%, as it is written here. So the number of emitted beta particles per second, we multiplied by the energy of the beta particles, but not the maximum energy, but the average energy, that is equal to 0.4 multiplied by the maximum energy of beta particles. So we know energy that is released due to the beta particles, and we divide it simply by the mass of human body. Of course, to calculate the equivalent dose, we also have to use the weighing factor for radiation type. But we remember that for beta and gamma radiation, this weighing factor is equal to 1. So in this case, we don't need to multiply it by this weighing factor. Okay, what about the gamma quanta? Again, I will repeat that these gamma quanta are released due to the annihilation of the emitted positrons. That means that the intensity of gamma quanta of this annihilation gamma quanta will be equal to two intensities of beta plus particles, because due to the annihilation of each positrons, there are two photons that are released. But we assume that only 50% of all the released photons will be absorbed in our body. That means that we have to multiply it by 0.5, and in this case it will be equal to the intensity of our beta particles. Thus, the amount of emitted gamma quanta will be the same, but the energy of gamma quanta will be different. And the energy of gamma quanta is 511 kiloelectron volt, as far as it is simply the mass of one electron. So thus the total, let's write it here, the total dose rate will be equal to activity multiplied by the intensity of beta particles divided by the mass of human body, and here it's just the energy of beta particles and the gamma quanta. Let's calculate it, just to not to take all these letters, all these annotations further. So I will write first all the numbers. Activity is 0.24 giga becquerels. Intensity is 0.97. Mass is 95 kilos. Energy is 0.4. Energy of beta particles here is 0.635 mega electron volts plus 0.511. It is mega electron volts, and as far as it is mega electron volts, we have to convert it to joules as well. So we have to multiply it by 1.6 to 10 to minus 13, because it's mega electron volt, and thus the dose rate in the 3 to 10 to minus 7 sievert per second. Per second, because it is becquerel, that is equal to 1 disintegration per second. Okay, so we calculate this dose rate in the initial moment. Again, to calculate the dose, in this case, we have to integrate the dose rate by time, but in this case we don't know the certain time for the radiopharmaceutical to be present in the human body. Thus, we should take the time from initial moment to the eternity, and also it is not simply lambda. In this case, it is lambda, so-called effective decay constant. So let's first make all the calculation with our integral. 0. And if we will take these limits for integration, these borders, we will simply obtain this expression. So quite simple. So it will be divided by natural log 2 And then we should stop at this moment, because we have to express our lambda. That is not just lambda, as I already mentioned. It is effective decay constant. That is a sum of decay constant due to the radioactive decay, and the decay due to the biological release of the compound. So it's bio. So that means that due to the radioactive decay in combination with the biological release of our compound, the time of the release of the reducing of the activity of our radionuclide in human body, this process is faster than just radioactive decay. So from this equation we can calculate that it is log 2 divided by with, let's say, take the index R due to radioactive decay and bio due to the biological release. If we simplify this equation, we will get log 2. Here it will be a product of these two half-lives, and it will be a sum of these half-lives in the upper part. So, and this expression we will use here. So log 2 will be here. Here it will be the sum of these two half-lives. And it will be a product in the upper part. So let's calculate it somewhere here, let's say. So D will be, so our dose rate 3 to 10 to minus 7 per second divided by log 2. Here is the sum of our half-lives. So let's write them first in minutes. So it's 90 minutes converted to seconds. So it's simply 60. And it will product of these numbers and also 2 times conversion from minutes to seconds. So let's calculate 1.2 to 1.3 10 to minus 3 sievert, or 1.3 millisievert. So you can see that even when we use such a high activity of the radiopharmaceutical, even in this case we will obtain the dose, equivalent dose that is equal to the average dose that we receive from natural background. At least in Moscow it is more or less the same dose. For annual average dose, and thus it is quite safe for the patient. So from this illustrative example you can see how all these calculations of the equivalent dose for the patient are performed. So this is all. Yeah. This is all for today's seminar, and See you next time.